you mind starting recording? Oh,
There you
perfect. You
go.
beat me to it. Excellent. Well, good afternoon and good evening, everyone. Welcome to the Thursday, October 31st HamSCIence Zoom call. Today, I think we'll get right into it. Gwyn Griffiths has, I know, an interesting talk. I got to see a little preview, and I'm sure the rest of the group will enjoy it very much as well. So, Gwyn, if you'd like, why don't you take it away?
Okay, thank you very much indeed, Gary. Let's fire up the technology.
Last Farming Fire, third dispatch on a public assist 205 Washington Avenue. Person locked out of the house, 16th row.
Yeah, just a reminder too, if everyone else could mute, that'll help. And then I know Gwyn's planning on taking questions at the end, so.
Yeah.
Which I need to do too.
Okay. Oh, maybe is the video of me in the way?
No, it's not.
Okay. If
But
it's
here,
technical.
Gwyn, I'm gonna mute everyone, but
Okay.
and then you're gonna unmute yourself, okay?
Unmute. There we go. Okay. Right. Well, good afternoon to you all and good evening here. And before I start, I'm going to say there is a Halloween-related word embedded in my talk, and there'll be a treat for the first person to spot it. So I really do welcome this opportunity to present work that's very much in progress, hence the steps along the way. And really, they may be actually more important or relevant or interesting than some of the outcomes. But preparing this talk has already helped me better structure my own thoughts, but it's left me questioning my initial assumption on whether I understood anything about high and low rays. And this upfront list of acknowledgements is there for the record, but it is also a really true tribute to HamSci connecting and enabling different communities to work together. So steps along the way are at the heart of this talk. The HamSci Personal Space Weather Station database at the University of Alabama and the quick look plots on the website are absolutely brilliant. But as we'll see, the data set is far, far richer than can be seen in the summary plots. Getting to the underlying data and working with it weaves throughout this talk. So I'll cover reading in Grape data from the digital RF files, how to calculate Doppler shift using a ridiculously simple algorithm, how we can separate out Doppler shift, amplitude, and frequency spread from different propagation modes into separate columns, and by calculating height of reflection, perform a reality check on the Doppler measurements and the assumptions we have made. However, the incredible richness of the Grape data sets bring complications. And in this case study, we'll meet bimodal Doppler spectra, where simple algorithms are just not appropriate. Now, many weeks of work have gone into trying different methods of separating propagation modes, and a robust general solution still eludes me. I suspect this is also a major challenge for HamSci professional researchers. Nevertheless, in this case study, I've made sufficient progress to share what appear to be credible results for bimodal Doppler shifts, but poses a conundrum when converted into reflection height and compared with predictions from PyLab modeling. So let's start with a quick look spectrogram for today's test case. This is all the data I'm going to concentrate on today. And I really want you to sit well back from the screen and burn into your memory the traces between 1400 and 2000 hours UTC. And I'll forgive you your quizzical look as you ponder, why on earth has it taken him weeks to examine these few hours from one plot at one frequency. Well, I hope by the end of this talk you'll have some sympathy for me. As befits a test case, this data has several nice attributes. It's a clean signal, and it looks to have a high signal-to-noise ratio. And those attributes make it amenable to this ridiculously simple algorithm for finding Doppler shift. There's some vertical banding from an unknown cause. I really don't know why it's there, but it shouldn't worry us. Neither should the ghostly traces. No, have you got it? Yep, right, okay. Yeah, the ghostly traces. I'm pretty sure that those are from the propagation mode 2-hop side scatter. So our first step along the way is, how do we read in data from the digital RF file? So having found the site and the day of interest on the Personal Space Weather Station website, we click to download the data, unzip the folder, and it'll automatically be named CH0. There's Get You Started code on the Digital RF GitHub site. Now here are the lines of Python code needed to get the data into a NumPy array. Nathaniel's RX888 was set up to record 9 time standard stations, and with the array index starting at 0 in Python, array index 8 is the frequency for 25 megahertz, which is what we want for today's talk. The data rate is 10 hertz, and so I'm going to read in 720,000 samples to take me from 00 UTC up to 2000 UTC. We set a data folder location, and we use 2 digital RF functions to get details on the channels in our folder and the start time, before the very simple read function gets it into the input array, and in which we'll have all the frequencies, and then this step extracts the column for 25 megahertz into that array data underscore 25 megahertz. And that's a series of complex numbers representing the magnitude and phase of the baseband signal centered at 0 hertz, a bandwidth of plus and minus 5 hertz. So those are the only lines of Python code needed to read in digital RF data. It's not difficult. So what does 1 minute of IQ in phase and quadrature, or complex numbers, real and imaginary parts at 10 hertz, of WWV at 25 megahertz look like at W2NAF? Because I really like to get a feel for the actual data that I'm working with. What does the time series look like? Now, this simple time series plot showing the in-phase and quadrature amplitudes serve that purpose, and it reinforces my initial comment that this is a high SNR. You know, that could almost be coming out of your signal generator, but it's WWV at 2,600 kilometers. That's what the data looks like. Which means that this ridiculously simple algorithm to estimate Doppler shift can be used. Don't let its full title, Argument of the Complex Autocorrelation at 1 lag, put you off. So expanding our time series, let's just take 2 samples. That's all we're going to need, 2 samples. One at time t, and the next one at time t plus delta t, where delta t is the sample interval, which here is 0.1 seconds. Now we're going to form the complex conjugate of the second sample. All that involves is simply changing the sign of the imaginary part. Now we can plot the first sample here on the complex plane on the right. That's S of t in green. and I'm plotting its the complex conjugate of the sample at times t plus delta t down here as the triangle. Next, we multiply our complex signal at time t by the complex conjugate at time t plus delta t, and here I'm plotting it as the magenta diamond. Now, we take the phase angle of the result, so that's the argument of the complex number in the magenta diamond, and where the angle 0 is along the positive real axis. And that angle gives us minus 36 degrees. Then we divide that by the number of degrees in one cycle, which is 360. And the sample interval, 0.1 hertz, and it calculates the frequency as 1 hertz, which is what I started with. So using this simple algorithm with the complex name of argument of the complex autocorrelation function at 1 lag, we get the frequency from just 2 samples. Now, in reality, I'll average the correlation function over 600 samples, which is 1 minute, to get a Doppler shift for a real-world signal. But it's that straightforward. So what do the results look like? So, and also in the time domain, I can estimate the signal level by adding the mean and root mean square values in each 1 minute interval. So recalling the spectrogram from the Personal Space Weather website, you won't be surprised to see 2 regions. So these are signal levels up in the top graph from 2 quite distinct propagation modes. They have the distinctive and non-overlapping signal levels. That's key. The high signal level is from 1-hop propagation in orange, present before the 25 megahertz band opened for 1 hop, and as the eclipse temporarily closed the band, and with a signal level some 40 dB lower, in brown, the propagation mode was most likely 2-hop side scatter. Now, PyLab modeling on the bottom right suggests that the scatter was over the Gulf of Mexico. That's the region where transmit rays from WWV and simulated transmit rays from Nathaniel's location overlapped. That's not really the talk today, but what we're looking at are 2 distinct propagation modes, and this very simple algorithm on that data is good enough to pick out the Doppler shifts associated with those. So we easily separated the Doppler shifts because of the amplitude difference of 2 propagation modes, because they are non-overlapping. We can also identify and separate using frequency spread. So we're still in the time domain, and it can be estimated through the magnitude of the correlation function, not its argument, not its phase, but its magnitude. The tricky part is estimating the noise n, which I've assumed to be 0 in this very high SNR example. And I also can't find whether the width is 50%, 90%, or something else. So I need to find that. So in this time series, we again have a clear and non-overlapping distinction between 1 hop with very low frequency spread and 2-hop side scatter with much greater frequency spread, and a difference between the frequency spread from 2-hop side scatter well before the eclipse, the normal circumstance, and then the very special circumstance of at the peak of the eclipse, which I'd not seen before. But we can easily separate in this case based on frequency scatter, the propagation modes. And we can work through to calculate reflection height. So I'm still building up my intuition for interpreting Doppler shift, not helped by its dependence on frequency, but converting Doppler shift to reflection height removes the frequency dependence and enables me to compare expected diurnal changes with ray trace models such as PyLab. Here, I've essentially followed the method in the paper by Christina Collins and colleagues. My initial height here, 240 kilometers, is from PyLab, but with some concern as I had to use a smooth sunspot number of 170 to get the path to open at 1420 UTC, rather than the accepted smooth sunspot number for April, which was 103. Nevertheless, the expected features are present. The morning descent, bottoming out, and then a rise in the height of reflection at the start of the eclipse, with a height rise of at least 38 kilometers, the band closing due to the eclipse before the expected turnaround in height of reflection. And so we have a credible picture of the change in reflection height from Doppler shift calculated by the very simple autocorrelation algorithm. Now here's an aside. Before we leave the algorithm, let's look at the results on a 7-kilometer through line of sight path between WWV and two co-located Grape receivers. Through the commitment and effort of Dave Swartz, W0DAS, and colleagues, we have results from a Grape 1 DRF reporting as W0DAS on the left, and a Grape RX888 Whisper Demon reporting as WW0 WWV/0 on the right. Now, on the left, the frequency shift from exact 10 megahertz for the Grape 1.2 is about minus 11 millihertz. And I suspect it's most likely from an uncorrected sound card oscillator, a frequency not truly precise. Now, in addition, Dave uses a horizontal dipole for this receiver, and I suspect the greater variation in frequency shift and the bump in frequency spread were likely from multipath from near vertical skywave. Despite only being 7 kilometers distant, this path had multipath from NVIS at 10 megahertz because of using a horizontal dipole. Now on the right, we see the Grape RX888, only dependent on a GPSDO for its frequency accuracy and stability. And we have impressive results, a mean offset of 0.28 millihertz and an RMS variation of 0.16 millihertz. That is 1.6 parts in 10 to the power 11. There is no evidence of multipath, partly I think because the antenna here is a vertical. So this reference site close to WWV reconfirms the Grapes as high-precision scientific instruments. For the very highest performance, use an RX888 and GPSDO and seek to avoid multipath. Earlier, I suggested you sat back. Now's the time to peer closely at the zoomed-in spectrogram from the PSWS website. There are quite distinct, for want of a better description, loops as the band opened and as it closed. There were other times at which the Doppler trace was likely bimodal, for example here and here. And so you might well ask, might the Doppler shift not be bimodal throughout, just that we cannot separate at this resolution? So the implication is that there were two propagation paths. What could they be? Now, I thought there were clues as to what the two propagation paths might be in this ray trace that HamSCI just happens to use in its publicity material. So this is for 15 megahertz, but the principles are the same for our test case at 25 megahertz. There is a skip zone where one hop propagation is not possible. The ray that propagates to the very edge of the skip zone is not the ray with the highest elevation. That ends up here on this blue arrow, well beyond the actual edge of the skip zone. The highest ray would be the one at the edge of the skip zone if the height of reflection did not change with takeoff angle from the transmitter, but it does. Rays at higher takeoff angles are refracted higher up in the F region and consequently reach a greater distance than rays at somewhat lower takeoff angles. So the implication is that for a certain distance beyond the edge of the skip zone, there will be two rays reaching a receiver, one from a relatively high angle and the other from a relatively low angle, and they will not have been reflected from the same height. Now, one of the beauties of PyLab is that we can add some Python code to extract other variables. So with a few lines added, I've extracted the distance at which rays for a span of elevations, here in 0.1 degree increments, and these are elevations, or you can think of it takeoff angles from the transmitter. So this is the distance at which they reach the ground. And here is a plot of the data for 1420 UTC. Just as the path from WWV to Nathaniel opened at 25 megahertz on the 8th of April. Now from the PyLab model, it's the X, or extraordinary wave, here in red, that was first received. And at the very nose, it's from a single elevation angle. But a few minutes later, the nose of this plot would have moved to the left. The signals would be received at a shorter distance. And here's that picture for 10 minutes later. So we'd actually expect 4 propagation paths, an O and an X at the low, and an O and an X at the high elevation angle. But the O and the X, at least in PyLab, cluster together. The difference in elevation angle between them being much smaller than the difference between the high and the low, at least after a few minutes. So it's possible we'd only be able to differentiate between the wider separated low and high rather than the O and the X at each of those. Now separating the O and the X, that's where you might do with a polarimeter, and that would be terrific work for the future with coherent 2-channel receivers. So to separate closely spaced Doppler shifts hinted at in the PSWS spectrogram, we need some custom frequency domain analysis. And earlier we saw how to read in an IQ time series at 25 megahertz. And these are just a few lines of Python code that perform a fast Fourier transform on a hand-windowed data in chunks of 1 minute. FFT shift is used to move the zero frequency to the center for plotting. And here are 4 spectra spanning just 10 minutes. And as an aside, the continuous time series from the grapes is just so valuable in these studies. The changes in the ionosphere that are happening here over just a few minutes, and the grape data captures it so nicely. So at 1420, we had a broad low peak, centered at around plus 0.5 hertz. And this is the signature of 2-hop side scatter propagation. 4 minutes later, Superimposed on that broad hump, that hasn't gone away, we have a single narrow peak from one hop propagation along the great circle. This is just as the path opened. That peak is so transient. For just 2 minutes later, we now have 2 peaks, and the signal level has gone up by about 20 dB. 4 minutes later, the separation of the peaks has increased and the level of one has dropped. There's absolutely no sign here of 4 peaks, the O and the X for each of the highs and the lows. These are real dynamic changes in the ionosphere. So plotting spectra is all well and good, but what I really need are time series of Doppler shifts at the 2 spectral peaks. Now, for me, this has been truly a non-trivial task with quite a few dead ends along the way. Let's go through the problem step by step with this example spectrum for 1800. Our eyes see 2 well-separated Doppler peaks. Having tried a simple inflection algorithm, then a method based on kernel density estimation. I apologize for the jargon, but you can look up those terms later. I've settled on a function in Python's signal processing toolbox. The function is called find_peaks_CWT, where CWT is an acronym for continuous wavelet transform. So I'll outline the CWT approach in the next slide. But for now, what's key is that the function lists the indexes of amplitude maxima. And from those indices, I can get the appropriate frequency bin. So we now have Doppler in increments of 1/60th of a hertz from our FFT. For a higher resolution, I can use a 3-point interpolation. No wider, as we don't want to contaminate one peak with another if it's closely spaced. So we now have digital Doppler estimates for 2 co-propagating paths with a resolution of a few millihertz. So a little bit on the continuous wavelet transform. If we think of the more common FFT as a method of fitting sinusoids to a signal, in a continuous wavelet transform, we fit a wavelet with a range of widths. Now, one can choose from a number of different wavelengths, although the default in this toolbox, the Ricker wavelet, also known as the Mexican hat or the sombrero, is well suited for finding peaks. The actual Python code is straightforward, but in use, it's not entirely satisfactory. We have to tune the range of these widths based on the characteristics of the dataset. To be specific, I found that with a minimum width of 1, there would be instances of false peaks from narrow spikes close in to either the true first or second peak. And if the maximum width was 4 or more, was more than 4, the algorithm would ignore the normal narrow peaks that we've seen. They would not appear in enough of the specified range of widths to be accepted. So having introduced the continuous wavelet transform as working well for the spectrum at 1800, here's the same test case data set with 2 examples where it fails. On the left, the algorithm got the second peak completely wrong. It ignored the higher level peak nearby, and it also ignored this close-in peak just to the HF of the true first peak. So consequently, in this case, where the second peak was a very low level and far removed, I added some code to try with the minimum width of 1, and in this case, it did find in the zoomed in view the true second peak. So at 1459 UTC, recalling that the minimum width here was 2, the algorithm reckoned the second peak was down here. Again, totally wrong. Now it rightly ignored these small peaks on the side of the main one, highlighted with those arrows. Now my guess is that the second peak is actually what looks like a shoulder here. The second peak at this time is so close to the first that there was no way that this algorithm was going to pick it up, even with a minimum width of 1. So this is not a truly robust solution. That still evades me. So having used those methods now, doing the best that we can with the continuous wavelet transform, here's what the first hour or so of the bimodal Doppler data looks like. So here we've got the zoomed in loop from the PSWS spectrogram. That gave us the clue as to what was going on. But now we have in exquisite detail the digital values of the Doppler shift as 2 time series. So recall that the methods so far have only assigned labels, first and second peak, by their amplitude. Now, I'd expect continuity for the 2 traces, for one of them to be the open circles, the first peak, and the other one to be the blue dots, the second peak, but they're jumbled up. So neither the postulated low ray or the high ray, the first or second peak, always has a higher signal level. They're jumbled up. So now we've got to separate them. As an aside, on amplitude, it's not terrific that Nathaniel's antenna, you see, an off-center fed dipole in this orientation, is working on a side lobe out to WWV. And what's more, it's on the very edge of the side lobe. And in azimuth and in elevation, we're working between 10 and 20 degrees here. So again, we're working on a lobe that's changing rapidly with angle. Its magnitude is changing rapidly with angle. And so, I mean, these are only model predictions, but it means that amplitudes are really hard to work with. And I do know that there is a recently formed HamSCI antenna project group that will look into perhaps a more optimum type of antenna. So separating and identifying high and low rays, what are some methods? So this is my amateur machine learning approach to ray Doppler separation. I want an initial training set of Doppler shifts correctly assigned to the postulated 2 rays. And a set of 10 seemed sufficient, for I'm after capturing short time trends within a highly variable natural phenomenon. And I thought that simple linear regression of the first peak Doppler values with time, followed by comparing residuals for the first and second peak, would suffice. Now, having got a training set, I then tried 2 different machine learning approaches for assigning subsequent peaks to set 1, and by implication, the second peak would get assigned to set 2. Now, it appears simple to use the training set to predict just 1 minute ahead, but it wasn't so. Again, in jargon, the support vector regression with radial basis function wasn't as good as something, believe it or not, that's out of Facebook and called Profit. So here are the 2 methods, and this is what they produce. So my first initial training set comes from the assignment of amplitude of the first and second peaks, and it gets 3 time intervals wrong. But by fitting this line, the regression line in black, it's clear which of the 3 points are attributed to the wrong ray. They've got much greater residuals than the other peak. So we can easily then form our first initial training set of 10 samples. Now, on the right is our second stage. the two machine learning algorithms predictions for one step ahead. The open circles are from the 10-minute training set. The solid black circle here is from the support vector regression, and it's way out. Facebook's profit gets that magenta spot there and also gives you its error bars. And so the actual point, which is the dark black circle, is reasonably close to the Facebook profit prediction. So in that case, we would accept that point as the next in our series rather than the second peak, which in this case was way down here in blue, but they're not always that different. So the outcome of this data and analysis and assignment for the first hour is in this graph. So we now have Doppler shift time series for the two rays with consistent data points, except for two values. So that one there and that one. So we've got a 97% success rate in attribution of Doppler to the two rays, entirely automatic. And I'm actually quite encouraged by this plot. I think it shows the exquisite measurement capability of the Grape receiver and some progress in data analysis of bimodal Doppler. Now, the misassignment with the red arrow, this one is most curious. The spectrum got the first peak right, but it just didn't find the second peak. I mean, that's such a clean, nice peak, but the continuous wavelet transform method just didn't find it. So I'm really curious about that. Now, I showed the nice data set the first hour. The rest of it is rather spotty. It gets the second ray lot wrong numerous times, but the first ray, the open black circles, it really is very good. So again, I'm encouraged with this. So earlier, I referred to the usefulness of deriving height of reflection from Doppler shift as a reality check, a diagnostic. So let's step through what the graph at left shows. The red and the green triangles are the heights of reflection from PILAP modeling for the extraordinary and the ordinary rays, for the low rays and the high rays. In magenta, buried in here, which I hope you can see, is the height of reflection based on the PILAP initial value, 240 kilometers, and Doppler shift from the autocorrelation algorithm, our very simple, very first step. And very credibly, it tracks the PILAP height of reflection for the low ray. The heights from the bimodal spectrum analysis, postulated as I initially thought with too much confidence, with the high and the low rays, for either side of the autocorrelation derived value, which is good in its way, but what I've called the high ray is nowhere near the high ray refraction height from PILAP. It's also the wrong shape. The PILAP trace is a magnified mirror image, and so I'm completely flummoxed. The change in height for the high ray from PILAP indicates that we should see a negative and large Doppler that reduces, but that it should start off at about minus 3.8 Hertz, this slope here, and reduces to minus 1.7. But there's nothing on the spectrogram, so it's nothing to do with my data processing. There's nothing in that spectrogram with those values. So, if not the high and low rays, what on earth are the two Doppler peaks that we see? Are they the X and the O? Is my method of extracting or interpreting reflection heights for the X and O rays at fault? So I end with these questions on the right. I've learned a great deal from these steps along the way about just how difficult it is to process bimodal, let alone multimodal Doppler spectra. And even when it ends up with a decent bimodal Doppler data set, it doesn't match my preconceptions. But heck, that's science for you. And I'll finish with some graphics from a 2023 report by Carano and Reno from Boston College on wave optics modeling of HF propagation. First, it's uncommon to see an arrival angle with range plot of the type I showed earlier. Second, the high ray in this model is flat-topped. It's not as exaggerated in its difference as there in PyLab. So is there something clue there? I'm trying to find hooks here. And finally, in the bottom right is a disturbed ionosphere. So we have a traveling ionospheric disturbance in their model. And look at what that does to arrival angle and range. So you'd see this whole plethora of Doppler shifts in a Grape receiver under these disturbed conditions. How are we going to measure and track them all? Thank you.
Wow, that was quite interesting, Gwyn.
Thank you so much, Gwyn. That was a fantastic analysis.
What are they?
Absolutely. I think we need to get on to polarimeter measurements, huh? But what's the for us experimentalists, right? I view myself as the experimental side of this. It looks like we need to get not just for antennas, we don't need just one. We need 2 or 3 cross
Gwyn,
polarize.
So first of all, I want to say that was an absolutely fantastic analysis. And I think that is probably the best analysis of Grape data and digital RF data I have seen to date. And I think and I think perhaps the one other person that has really opened my eyes to what this sort of thing is Steve Serwin. He's also just done absolutely amazing work. But I think you can probably appreciate from my point of view, there are many things that need to be focused on all at once. There is, everything from making sure that things are getting deployed properly to, do we take this microscopic view of the data? Do we take this more macroscopic view of the data? Just from your gut feeling on the project, is there one or two particular things on the project that would be really important for us to address right away that would make this a better data product or better?
Oh, it's with some trepidation that I try to answer such questions, Nathaniel. There really is superb data there. I think there's the stage of checking that the spectrograms really are clean.
Mm-hmm.
And I chose your data set, on purpose. It is a very clean data set, and for that day, to be sure, by even maybe the simple autocorrelation extraction of the Doppler would tell you if there was, it's a quick quality control. So if there was sort of a next stage of automated QC, even based around the simple autocorrelation algorithm,
Mm-hmm.
it might identify if any sites have an issue.
Mm-hmm.
And it clearly, I mean, I guess I've come to this Grape data because of my interest in frequency spread from FST4W, and becoming frustrated that an average every 2 minutes just wasn't telling me enough.
Mm-hmm.
And the Grape data gives me that. So
Mm-hmm.
that's where I've come from.
Mm-hmm.
And it clearly shows the RX-888 and the GPSDO current system really is such a quality scientific instrument with no uncertainty about offset or calibration. How one starts to tackle then the scientific analysis and the automated attribution to different propagation modes is an enormous challenge. But I think that's clearly where the science wants to take you.
Yeah, I agree with that. I think these are going to be things that are really worth thinking about. You probably, I mean, I know you know that we have this new Daisy 2 proposal that was funded and is officially going to start January 1st. And you probably know, and if that Christina Collins is hired as the chief operations scientist for, you did not know that.
No, I did not know that. No.
So the way we have it structured, the way we have the proposal structured is the data is again going to University of Alabama as it is, and the University of Alabama team has funding to improve the website and the data presentation tools on the website. So if there are things you don't like about the way things are done on the website, or maybe I should say if there are suggestions you have as to what the website should do differently, that those could be possibly accommodated. And Christina Collins is supposed to be the person that's working most closely with Alabama to see that those things are implemented and come up with those checking metrics. And it seems like the things that you're talking about here could be well utilized or would be appropriate to integrate into that part of the project. Yes, Mary Lou.
So in regard to the website, I had a suggestion, and Bill Engelke has now made it happen as of October 19th or thereabouts, just now. And that is to put grid lines on the graphs. So that is going to help us look at them better. I want him to change some of them, but at least we have grid lines of some sort.
Now, another thing to ask you, when you were doing this with PyLab, were you using which electron densities were you using? Were they the IRI electron densities?
It's IRI 2016 and using the full 3D PyLab for fully magnetoionic.
Okay. So I think a next step would be, you know, we have the SAMI 3 eclipsed ionosphere data. We need to make sure, unfortunately, Devin has graduated, which is good for him, but not good for us. But we need to figure out how to get you that data set so that you're not using the IRI and you're using something that is at least hopefully closer to reality. But when you're saying things like we're looking at right at the edge of, I really liked how you showed that my signal was right on kind of that marginal area of the nose, or you're like, you know, this highly variable area where you could move in and out very easily with arrays. You know, if you're just using the IRI 2016 model values, that may or may not be anywhere close to reality. And yeah, you may be saying, oh yeah, PyLab shows this supposedly big separation, but the actual ionosphere may not be that configuration at all.
Oh.
And so I think the next best thing we can do for you for modeling is to figure out how to get you those SAMI3 values, put them into PyLab, and
Right.
have you do the same analysis and see if it's still in that same marginal regime, or or is it going to match up with what you have better? So I think that would be really interesting to see.
Yep. Oh, I very much welcome that.
Yeah. Okay, we'll work on that.
Okay.
And then you should know, did you meet Jamal, Gwyn?
I'm not sure that we have. Maybe only in passing.
Yeah, maybe. So Jamal, he's in Egypt.
Right.
And he's been involved with us for about the last year or so, but we're just starting to get him kind of up to speed on Farlap and PyLap and things like that. So he's starting to do some modeling too. He's not quite at the point that you are yet, but he is very eager, and he's been working hard at things. So I have a feeling that that the two of you may be able to work together as we get Jamal moved. Right now he's on Farlap, hopefully get him onto PyLap, and then we can hopefully get you both the SAMI3 outputs for that.
Right.
Yeah.
Right.
But I think this is wonderful. I am so impressed at how you were able to separate those two different modes with such fine frequency resolution, and really see those different traces and pull that out. I just think that was fantastic. And it's both exciting and slightly disheartening that we look at it and you looked at like 2 hours worth of data, and I think about all the data we have.
Absolutely. Absolutely. Yes.
Maybe disheartening is not the right word. Maybe overwhelming is a better word.
But I was always in awe of scientists that could pull out the essentials of interesting physical phenomena from quite a limited data set. They didn't allow themselves to be completely consumed by gigabytes of data. They were able to find the little nuggets that spoke to the physics.
Yeah, I think you did that very well here.
Of course, that also brings up the question of, given all the data coming out of the last eclipse, of the solar eclipse QSO party, those millions of data points, what else? What other stuff is hiding in there that is yet to be discovered?
Yeah. The other thing I think that's interesting too is, along those lines, is, we can work at science in different scales. So I think you can look at, if we are able to take what you've done, Gwyn, and if we're able to refine it so that we are able to come up with an algorithm that can look at the data just, a couple minutes at a time, and effectively pull out, here's like the one elevation trace, here's a different elevation trace, and give us that, that information can then, it could be run across the whole data set if the algorithm's effective, and then that could reveal new things at a much larger scale that we haven't seen before. So I think it's really neat, and I'm hoping that we can we can see how to advance this.
So two questions this brings to mind. And Nathaniel, I know that Rachel's working on pulling together what do you call it, the science group on Friday mornings or some such thing.
Right.
Yeah, I mean, obviously I'm not involved with that, nor should I be. Would this be of interest to them? Because Gwyn's talk really hits a lot of points. Just a thought for you, that's all.
Yeah, oh my gosh, it absolutely would be for them. And we haven't quite gotten that group pulled together yet. And I'm actually uncertain that's going to get pulled together this year, because now we're going into November, and all of a sudden, at least I know I have a lot of travel, which we'll see you at the NASA Citizen Science meeting, and then and we have finals and the AGU and stuff like that. But I'm definitely, I'm absolutely going to recommend strongly that Rachel and the other Case Western people watch this video, because I think it's really, really an important video for them to see. And I think Rachel did ask this morning if it was going to be recorded, Gwyn. So I know that some of them have like class conflicts, but we tried to advertise it this morning, and she did say, is it going to be recorded? And I'm like, yes, it will. So we'll make sure we send it on to them.
Yeah.
The
And
second thought I had is for Rob Robinette. I mean, Gwyn made some interesting comments about the antenna patterns, and sort of kind of their effect on the analysis. So what I would like to do is, once the recording is up on YouTube, Rob, I'd like to put the link in our antenna group forum so that others in that group can see it, because I think there's really some interesting points for them to take away.
Yeah.
Yeah, I hadn't
I agree.
appreciated that. Yeah, I didn't appreciate the challenges introduced by a horizontal antenna. I mean, we had already pretty well established on a vertical omnidirectional antenna, but I think Gwen has pointed out in this presentation the importance of omnidirectionality. You know,
Yeah.
of course, it doesn't. There's still angle of arrival problems. You know, and the vertical is does not have uniform vertical.
Yeah.
So it isn't there's no perfect antenna. So
It's like a point source. There's no such thing as a perfect point source, nor is there perfect antenna in free space.
Yeah.
So,
Yeah.
One thing I'll bring up for antennas, it'd be nice to know what direction things were coming from. So we might consider, if we had 2 channels, we'd use cross loops. Or if we had 3, you could even do 2 cross loops and a near field antenna.
Of course, if
which
we
has
have
its attractions.
we get the the phase locked dual channel or multi-channel version of the chameleon or Clementine, then we could synthesize and afterwards do a processing and determine the arrival angle, irrespective of the patterns of the, you could synthesize the patterns afterwards. But getting that kind of a receiver into our project is a long-term task, I think.
Nathaniel,
Yes.
as I'm sitting here listening to all this, and given the amount of raw data that we have at our disposal, the thought occurred to me to get hold of some computer science people, because it sounds like some of this number crunching would be a really good project for an AI system.
Well, I think, we do have some of those people working on the team, and this also kind of speaks to how the team is structured.
Yeah.
So like the University of Alabama group that is holding the database, that's a computer science department. So we do have, Bill Engelke's group, they are computer science people that are looking at this and can kind of do that. I have some colleagues at Scranton that are computer science, and they're starting to think about these things too. But I think it's a great idea. And I mean, even Gwyn was trying to use some machine learning in his presentation today. He spoke a little bit about that and used at least 2 different techniques. So I think that's all really good. And yeah, I think there's.
Yeah, that would not only would it be good for us, but for the students as well, to get a real world project to get some grades on.
I think that's where I think that's also where getting like Christina Collins as a chief operations scientist working with the Alabama team and trying to integrate some of these ideas at that like database central server level is a good thing, because if the more that we can introduce some of these processing techniques at that central location, the easier it will be to apply them uniformly to all of the data sets and make it available to the general community.
Yeah. Okay.
Our Whisper Demon group has a AI expert, Stu Ogawa, in it, who has made some, I think, stabs at applying machine learning. But I think Stu needs he also is a full-time professional, but he also needs more direction and context. So if there were a specific a group within HamSci that were looking into applying machine learning. I mean, it was specifically not general, but machine learning applications informed by analysis like those that Gwyn is doing today. I think that Stu might be more productive than he's been able to be so far.
Yeah.
So, if something gets organized, let me know, and I will reach out again to Stu and see if he couldn't help us. And
So as I sit back and try to take in at least some of what Gwyn covered today, a lot of it's over my head, but I think the beauty of it is not only do we have some information on our past data, on some new analysis and new things to look for, but as Mary Lou and others have taught us, there's a lot more questions that come out of it. And Gwyn obviously said that right at the end of his slide. We've got more questions, so it's the discovery of all that, I think, is interesting to watch. It sure is.
So one of the
Any other-
people who's really interested, so this is for Rob, one of the people who's really interested in machine learning is Bill Engelke. And he's got several ideas and he's tried several and who have not worked, but he's really interested in that. And our former student, Nick Callahan, who is very interested in that and fairly knowledgeable, he's part of the group as well. So I think we ought to have a group on machine learning.
Yeah, this is not a new idea, I'll point out. We at here at Dartmouth, Jim LaBelle studies auroral roars, and it's really hard to pick those out without a human eye. Be very nice to be able to recognize phenomena through machine learning. And it's actually an interesting question whether we would see auroral roars down this far. They actually propagate north of the auroral oval, but with
What are they?
Solar Max, sometimes the oval is south of us.
So David,
Right.
what are these things he studies?
They're called auroral roars. They're
Roar?
harmonics.
Like a lion?
Yes, like a lion, exactly. And
No,
what
like a
they
bear,
are
like
is
a bear.
they're harmonics of the electron cyclotron frequency, which up where these occur is around the 1.5 megahertz. So the second harmonic appears at just shy of 3 megahertz. And then there's one shot just shy of 4.5. We've seen them up to maybe the fourth harmonic when things are very strong, and that would happen during the day, the lower ones usually at night. It's a mode coupling between various modes in the plasma. So these the electrons that are cycling around the magnetic field couple into another mode, and then it gets propagated to the ground.
We do have a receiver up near the magnetic North Pole,
Right.
which VY0 ERC. And if there are, right now it's doing Whisper and mostly Whisper and WWV recordings, but it seems very stable and sensitive now with the new antenna installation. So if there were other phenomenon like the roars you're describing that would be useful, we could set it up to to do continuous recording of those frequencies.
That's a really good idea. And we're also looking for conjugates between the northern and southern hemispheres.
Well, Paul and I shipped off the system for DP0 GVN that's going to the Neumeier. So we'll have another Whisper Demon and I included a 4 terabyte hard drive just so that it could do long-term recordings of phenomena like the ones you've described, David.
I'm going to have to say 73 because it is important that I take certain people out trick-or-treating. And I'm really looking forward to that. But thank you so much, everyone. I hope you all have a very happy Halloween. So
Bye-bye.
Thanks,
thank
Nathaniel.
you.
Right, bye-bye.
Thank you again.
Thank you again, Gwyn.
Thank
Okay,
you,
my
Gwyn.
pleasure.